All right, in this example, we have a rising balloon. A balloon is rising vertically above a level straight road at a constant rate of 1 foot per second. Just when the balloon is 65 feet above the ground, a bicycle moving at a constant rate of 17 feet per second passes under it. I'm really excited that these rates are identical, otherwise I'd be in trouble. How fast is the distance between the bicycle and the baboon? How about balloon? uh, I'm missing an L there. Balloon, uh, distance between the bicycle and balloon increasing 3 seconds later. Ooh, okay. So let's start by identifying what's going on. What are some of our major players in this problem? So step one, we have the height of the balloon. That's important. Balloon, baboon. Next, we have the ground distance because the bicycle's running along the ground. So we want to know what is the ground distance of the bicycle. And there's a cool little graph right next to us, so I might as well use that. S we're going to use, because we got S of 2. S we're going to use as the distance between the balloon and bicycle. Those are our major players. Okay. And they were kind enough to make a drawing for us. Oh, that's so nice of them. Okay, so we know that this is h, so this is the height of our balloon. We also have some ground distance. I'm going to make that green. And then we have s over there, sitting right here. So that's s. Great. Let's get some other information. We know what the rate is for our balloon. So that is our dH over dt equals 1 foot per second. We also know that we care about when the balloon is 65 feet above the ground. We also care about where the bicycle is. Now, we also need the rate of the bicycle. So we know dg over dt equals 17 feet per second. Now, we also know something about t, oddly. This is one we're actually getting a time, where t equals 3 seconds. So the time that we're looking at is not actually what we have right here. We're actually looking 3 seconds into the future. And 3 seconds in the future, things have moved because the bicycle is underneath the balloon. So the bicycle is right here, and then 3 seconds later, we have this picture. Ooh, so we need to readjust our picture. So if the bicycle has been moving for 3 seconds and it's moving at 17 feet per second, we know this is going to be 3 times that 17, which is 51. Oh, 51. Oh, you can't even read that. 51 feet. That's how big that is. Ooh, and the balloon is moving too. It's gone up 3 feet because it's only moving 1 foot per second. So it's gone 3 feet up. So our height is actually 68, not 65. Oh, how sneaky. Um, let's see, I've got the 65, I got the 17, I got the 1 foot, I got the 3 seconds. I think we've got everything into our diagram. Excellent. Now, what are we even looking for in this thing? So this was all step 2. How fast is the distance between the bicycle and balloon increasing 3 seconds later? So what is our change between those two things? What is our ds over dt? Okay. All right, let's start solving this thing. So to do that, we need an equation. So the other ones were like volumes, but this one doesn't seem to be that. This one is a right triangle. So we can use the right triangle distance formula because we're actually looking for ds over dt. So it'd be really great if we started with an equation that actually had s all by itself to begin with. Oop. No, I'm just going to keep that. It's fine. So our s is going to equal the square root of the height plus the ground distance squared. Now, unfortunately, in all the other ones, I was able to convert this so that I only had a single variable, but I don't know anything about the relationship between the height and the ground distance. I know stuff about their rates, but I don't know anything about the relationship between the height of the balloon and the ground distance of the bicycle. Since I can't get this so it is only a two variable equation, we're just going to leave it as 3 and it's going to be fine. So don't worry about it. I just got a little more implicit differentiation. That's all. So we end up with ds over dt equals stuff. We need to do the derivative of that square root. So that is going to follow the power rule. So I'm going to get a 1/2 in front. And all of that stuff is going to end up in the denominator. So I'll get a negative 1/2 exponent. So all of those pieces are going to go into my denominator. So I get a square root of h squared plus g squared. Now that I've done that, I need to do the derivative of the inside. So I need to do the derivative of h squared plus g squared, and I'm going to be doing that with respect to t. So the derivative of h squared is going to be 2h dh over dt. Then I got to do the derivative of g squared. That's going to be 2g dg over dt. Cool, I got that all right. Check my answers. All right. Now we've got this big gross function, but we actually know almost all this stuff. The one thing that we don't know is ds over dt, but that's okay. That's what we were looking for in this thing. So start plugging in some numbers. So we get 1 over 2 square root, a couple things squared. Our height at the moment that we're interested in, the height of the balloon at that time is 68. The ground distance of our bicycle at that time is 51. Then we get 2, some sort of height, and then dh over dt. The height of our balloon is still 68. And then dh over dt, it is still traveling at that speed of 1. So this thing is that thing. Then we've got 2g dg dt. Our ground distance of our bicycle is still 51. And the height of the speed of the bicycle is maintaining that 17 feet per second. All right. Well, let's see what this all this stuff equals. You can grab your calculator. This whole chunk ends up getting 1,870 divided by 2 times the square root of 7,225. 68 squared plus 51 squared. The square root of 7,225 actually is a nice number. You end up with, once you type this all in, and if you hit math fraction, it actually works out, you get 1,870 over 170. Then we can actually divide that. 1,870 divided by 170 ends up being 11 feet per second. I'm not going to write it out, but you can get that. You want to interpret that answer correctly and say that 3 seconds after passing under the balloon, the change in distance between the bicycle and the balloon is increasing at a rate of 11 feet per second. The distance between the yeah, I think I said that right. The distance between the balloon and the bicycle is increasing at a rate of 11 feet per second. Yeah, 3 seconds after passing under. Yeah, did that. Great. And that's it for today. It might have been a long time ago, but remember Newton's method. Newton's method is a quick way of kind of like checking our how the calculator figures out these exact values. And then remember the 6 steps of evaluating these related rates. Number 1, get those variables. 2, draw a picture. 3, write an equation and identify what is the thing that you're trying to find. 4, differentiate both sides implicitly with respect to time t. I think I was actually doing that as step 5. And then our step 6 was substitute. I kind of added an extra step. So sue me. And then finally, interpret your solution. Really make sure that you're saying what that value means. Don't just say, my answer is 11, or my answer is 11 feet per second. That's not what AP is looking for. It's looking for you to say, at a particular time, this is what's happening, and this is our rate with correct units. Thank you so much for watching. Hopefully you check out that bonus video that's also posted on Schoology, and you have a good day. Bye-bye.